Today's topic Today's topic is chemistry of noble gases from modern inorganic chemistry. The elements helium, neon, argon, krypton, xenon and radon comprise noble gases. The group of noble gases is regarded as zero group or group 18 of the periodic table. These are gases at ordinary temperature and do not have chemical reactivity. Due to chemical inertness, these were called inert gases. However, nowadays, a number of compounds of these gases, particularly of xenon and krypton, have been prepared. This shows that these gases are not completely inert. Consequently, these gases are called noble gases instead of inert gases, which signifies that these gases have some reactivity. Because of the low abundance of these gases on Earth, they have also been called rare gases. Occurrence of noble gases. The noble gases occur only as minor constituent in the atmosphere. Due to the inert nature of these gases, they always occur in the free state. Except radon, all these gases are present in atmosphere in the atomic state. The amount of noble gases present in atmosphere is given below. Helium 5.24 into 10 to the power minus 4, neon 1.82 into 10 to the power minus 3, argon 9.34 into 10 to the power minus 1, krypton 1.45 into 10 to the power minus 3, xenon 8.70 into 10 to the power minus 6. Helium is also present in natural gas to the extent 2 to 7%. It is also present in small quantities in minerals of radioactive elements such as monazite, clavite, pitchblende, etc. Helium, neon, and argon are found in the water of certain springs. Radon is radioactive and does not occur in the free state because it decays very rapidly. Helium was first discovered in Sun's atmosphere. It is now known that helium is being constantly produced in Sun's atmosphere by nuclear fusion reaction involving the formation of helium nucleus from 4 hydrogen atoms. History of discovery of noble gases. Noble gases are present mostly in the atmosphere. Their discovery is briefly discussed as follows. Discovery of argon. The main credit for the discovery of first noble gas argon goes to Cavendish. In 1785, Henry Cavendish performed a number of experiments to determine the composition of air. He passed repeated electric sparks in a dry sample of air with an excess of oxygen to convert nitrogen of the air into nitrogen dioxide according to the reaction. The gaseous mixture containing nitrogen dioxide and unreacted oxygen was absorbed in alkaline potassium sulfide solution. He observed that a small amount of residual gas, about 1 by 20th% of the original volume of air, was always left behind. He repeated the experiment again and every time observed small traces of residual gases, which was neither oxygen nor nitrogen. He could not understand the nature of this residual gas, which could not combine with oxygen. However, the observation of Cavendish remained unnoticed for over a century. In 1894, Lord Rayleigh observed that the density of nitrogen isolated from the atmosphere is about 0.47% higher than the density of nitrogen prepared in the laboratory by thermal decomposition of ammonium nitrate. NH4NO2 gives N2 plus 2H2O. This minor discrepancy would have been ignored by many investigators. Then Rayleigh, in collaboration with Ramsay, repeated the earlier experiments of Cavendish and concluded that the residual gas contained a new gas different from nitrogen. It was examined carefully by spectroscopy and was found to be an unknown gas. The new gas was named argon. Greek argos mean inert or idle. Discovery of helium. Helium was first detected spectroscopically by Lockyer in Sun's atmosphere in the year 1868 while examining chromosphere of the Sun during total eclipse. As a result of their investigations, they concluded a new element called helium, Greek helios meaning sun. Later on, Ramsay in 1895 also detected the gas on Earth from radioactive mineral clavite. Kaiser in the same year detected helium in traces in the atmosphere. Discovery of neon, krypton, and xenon. Ramsay and Travers performed certain experiments on argon, suspecting it to be a mixture of a number of similar constituent gases. They repeated experiment on liquefaction of air and its fractional distillation. The first fraction was found to contain new element which gave a different spectrum. The element was called neon, Greek neos meaning new. Shortly afterward, they discovered two or more new elements on further fractional distillations called krypton meaning hidden and xenon means stranger. Discovery of radon. Radon was discovered by Dawn in 1902 as a result of the study in the disintegration product of radium. Position of noble gases in periodic table. While building up the periodic table of elements, Mendeleev had not left any space for the noble gases. Obviously, he could not imagine the existence of elements which have almost no chemical reactivity. Ramsay, the main discoverer of these gases, proposed a new group for these elements on the basis of their atomic masses and lack of chemical reactivity. This group is called zero group of the periodic table. The zero group also suggests chemical inertness or zero valency. Before the discovery of noble gases, there was a sudden change from the most electronegative halogen on right hand side to most electropositive alkali metals on left hand side in the periodic table. The addition of zero group between 7A group and first A group has solved this anomaly. The position of noble gases in the periodic table was later on confirmed by Moseley, who constructed the periodic table on the basis of atomic numbers. The values of atomic number of noble gases strongly suggest that they should be placed after halogen and before alkali metals. Generally, characteristics of noble gases. Electron configuration. Except helium, the atom of all noble gases have 8 electrons in the valence shell. The general electronic configuration of noble gases except helium may be expected as Ns2Np6. Helium has the electronic configuration 1s2. This configuration being stable, the noble gases neither have any tendency to gain nor lose electrons and therefore they do not enter into chemical combinations. It is therefore reasonable to assume that the inert nature of noble gases is due to their stable electronic configurations. Physical properties. Some of the important physical properties of noble gases are given in the table. First, existence. All the noble gases are monoatomic, colorless, and odorless. The monoatomic state of these gases is due to stable electronic configuration of their atoms. As a result, they are not capable of combining even amongst themselves. The monoatomic nature of these gases is confirmed by their values of Cp by Cv, where Cp and Cv are the molar heat capacity at constant pressure and constant volume equal to 1.66. It is observed that for all monoatomic gases, Cp by Cv is close to 1.66. Atomic radii. In the case of noble gases, the atomic radii corresponding to van der Waals radii. As we go down the group, van der Waals radius increase due to addition of new electronic shells. Ionization energies. The first ionization energies of noble gases are very high. This is attributed to the stable, completely filled configurations of noble gases. However, the ionization energies decreases with increase in atomic number from helium to radon due to increasing atomic size. Electron affinities. Due to the stable Ns2 and P6 electron configurations, noble gas atoms have no tendency to accept additional electron. Therefore, their electron affinity is nearly zero. Melting and boiling point. The melting and boiling points of noble gases are very low in comparison to those of other substances of comparable atomic and molecular masses. This indicates that there are no strong attractive forces between the atoms which may hold the atoms together in the liquid or in the solid state. It has been established that only weak van der Waals forces are present between the atoms of the noble gases in the liquid or the solid state. These van der Waals forces are increased with the increase in atomic size of the atom. Therefore, the boiling point and melting point increases from helium to radon. Ease of liquefaction. The noble gases are not easily liquefied. This is due to the fact that there are only weak van der Waals forces which hold atoms together. This is also clear from low values of heat of vaporization of these gases due to increase in atomic size and therefore increase in van der Waals forces. The ease of liquefaction increases down the group from helium to radon. Solubility in water. The noble gases are only slightly soluble in water. The solubility in general increases from helium to radon. The solubility of noble gases in water is due to dipole induced dipole interactions. Water is a polar molecule. When it comes near a noble gas atom, it induces dipole in the noble gas atom by distorting or polarizing the symmetrical electron cloud of noble gas atom. As a result, an induced dipole appears on the noble gas atom, leading to interactions with the dipole of polar water molecule. Therefore, because of dipole induced dipole interactions between water molecules and noble gas atoms, the noble gas dissolves in water. As the size of noble gas atom increases, the extent of polarization also increases. Consequently, the magnitude of the dipole induced dipole interactions increases, and hence the solubility of the noble gas in water increases from helium to radon. General chemical characteristics. In general, noble gases are not very reactive. Their inertness to chemical reactivity is attributed to the following reasons. The noble gases have completely filled ns2 and p6 electronic configurations in their valence shells. The noble gases have very high ionization energies. The electron affinities of noble gases are almost zero. Therefore, they have neither tendency to gain nor to lose any electrons and do not enter into chemical combinations. However, in recent years, it has been found that noble gases, particularly xenon and krypton, form some compounds. Chemistry of compounds of noble gases. Prior to 1962, it was believed that noble gases do not combine at all and no compound of noble gases were formed. Though from time to time some attempts have been made to test the reactivity of noble gases, yet the gases were thought to be inert. This was also supported by the following reasons. The atoms have stable, completely filled electronic shells. They have high ionization energies. The noble gases have almost zero electron affinities. Therefore, they do not have any tendency to gain, lose, or share electrons with other atoms. The above reasons discourage the chemists to make serious attempts to prepare compounds of noble gases. In 1962, N. Bartlett, while investigating the chemistry of PTF6, noticed that platinum hexafluoride acts as a powerful oxidizing agent which combines with molecular oxygen to form ionic compound dioxygenyl hexafluoroplatinide. This indicates that platinum hexafluoride has oxidized oxygen to oxygen positive. Now, oxygen and xenon have some similarities, and this led Bartlett to try reactions between xenon and platinum hexafluoride in a similar manner. For example, the first ionization energies of xenon gas is comparable to that of oxygen for this process. The molecular diameter of oxygen and atomic radius of xenon are almost same, 4 angstrom. With this assumption, Bartlett reacted xenon and platinum hexafluoride in gas phase and an orange-yellow solid xenon hexafluoroplatinate of the composition was obtained. On analysis, this compound was found to be an ionic compound, and this marked the first compound of any noble gas. The formation of this ionic compound has demonstrated that xenon is not totally inert and it is possible to remove an electron from xenon atom. This discovery attracted many scientists for active research for the preparation of other noble gas compounds. Within a few months, xenon tetrafluoride and xenon difluoride have been prepared in laboratories. This noble gases chemistry begins. Among these noble gases, xenon form a large number of compounds with fluorine, or with oxygen and krypton form only a few compounds. Some important stable compounds of xenon in different oxidation states are listed in table. Plus 2 xenon difluoride, xenon tetrafluoride. Plus 4, plus 6 xenon hexafluoride, xenon oxytetrafluoride, xenon difluoride, plus 8 xenon octoxide, xenon octafluoride, xenon tetroxide. Before discussing the chemistry of compounds of noble gases, it becomes important to understand the answers of some important questions. What are the factors responsible for late discovery of compounds of noble gases? Why do most of the compounds involve xenon, fluorine, and oxygen? Late discovery of compounds of noble gases. Prior to 1962, it was believed that noble gases do not combine because they have stable electronic configurations. Many attempts were made to prepare their compounds, but all these attempts proved to be unsuccessful. Motion in 1895 had reported that there were no chemical reactivity between fluorine and argon. This led Ramsay to conclude that the noble gases are chemically inert. This conclusion was also supported by the concept of valency. According to this concept of valency, the electronic configurations having 8 electrons in its valence or outermost shell has been taken as a criterion of stability and inertness. That is why the noble gases were assigned zero valency and this group was designated as zero group. However, the concept of octet configuration of noble gases suffered setback because of discovery of compound like PF5, SF6 and IF7 which had more than 8 electrons in their valence shells. This however did not make the scientists to make more serious attempt because the noble gas seemed to have neither any tendency to lose electrons nor any tendency to gain electrons. Some other factors in addition of chemical inertness of noble gases which led to late discovery of noble gases compounds are lack of availability of fluorine of good quality, non-availability of fluorine resistant greases, non-availability of inert material to handle fluorine gas, non-availability of large quantities of noble gases. Why do most of the compound involve xenon, fluorine and oxygen? We know that the tendency of an atom to lose electron is given by its ionization energy. If we see carefully, the ionization energies of these elements are given in table 1. It is noticed that leaving aside radon, which is unstable, only xenon and to some extent krypton has ionization energy comparable with common elements like carbon, nitrogen, and oxygen. Xenon therefore has the maximum tendency to lose electron and thus form the largest number of compounds. Krypton comes next, neon, argon, and helium, which have much higher ionization energies form hardly any compound. Further, since reactivity of xenon and krypton is due to their tendency to lose their electrons, it suggests that the combining atoms should have strong affinity for electrons, that is, should be strongly electronegative. Now, in the periodic table, fluorine and oxygen have high electron affinities and therefore have stronger tendencies to accept electrons from other atoms. It is for these reasons that xenon and krypton forms compound mostly with strong electron acceptors with fluorine and oxygen. The most of these compounds are fluoride, oxyfluorides and oxides. Xenon combined directly with fluorine, its compound with oxygens are obtained from its fluorides. Xenon chloride is known but it is not stable. Only one compound with nitrogen is known but it is highly unstable. Compound of xenon. Xenon forms a large variety of compounds with fluorine and oxygen in different oxidation states. These are xenon fluorides, xenon oxides, and xenon oxyfluorides. Let us discuss the method of preparations, their stereochemistry, and important properties of these compounds. Xenon difluoride ZeF2. Preparation. It can be prepared by the following methods. Xenon difluoride is best prepared by heating a mixture of xenon and fluorine in a molecular ratio 2:1 at 400 degrees Celsius in a sealed nickel tube. On cooling quickly, a colorless solid ZeF2 is obtained. Excess of xenon is used to avoid the formation of any higher fluoride such as ZeF2. It can also be prepared by subjecting a mixture of xenon and fluoride in the molar ratio of 2:1 to electric discharge. It is also formed by petrochemical combination of xenon and fluoride in the presence of mercury vapor. It can also be prepared quantitatively by fluorination of xenon by oxygen monofluoride O2F2 at -78 degrees Celsius. Properties. Xenon difluoride is a colorless crystalline solid which melts at 129 degrees Celsius. It is the least volatile of xenon fluoride. It is stable in pure and dry state and can be stored in nickel containers. It dissolves in hydrogen fluoride without reacting with it. It reacts with hydrogen to give hydrogen fluoride and xenon. ZeF2 plus H2 gives xenon plus 2HF. It gives substituent reactions with strong protonic acids. It hydrolyzes slowly but completely in acidic and neutral or alkaline solutions. It oxidizes iodine in the presence of BF3 to give IF. It reacts with NO and NO2. ZeF2 plus 2NO gives nitrosyl fluoride plus xenon. ZeF2 plus 2NO2 gives 2NO2F plus xenon. It reacts with sulfur trioxide to give xenon. ZeF2 plus 2SO3 gives xenon plus peroxydisulfuride difluoride. It is mild fluorinating agent, thus it reacts with benzene to give fluorobenzene C6H5F. It also fluorinates ethylene to give 1,1-difluoroethane. It is also a strong oxidizing agent. It oxidizes HCl to Cl2, Ce3 to Ce4, chromium 3 to chromium 6, and Bro negative 3 to Bro negative 4. Xenon difluoride in anhydrous hydrogen fluoride react readily with platinum metals, sulfur powder, and iridium to produce highest fluorides. Platinum plus ZeF2 in presence of hydrogen fluoride gives PtF6 plus 3 xenon. Acid plus 24 ZeF2 in presence of HF gives 8 SF6 plus 24 xenon. In BrF2 solutions, xenon difluoride acts as a Lewis base and forms a duct which compositions ZeF2.mf5, ZeF2.2mf5 and 2ZeF2.mf5 where M is equal to P, arsenic, antimony, etc. For example, ZeF2 plus SbF5 gives ZeF2 dot SbF5. This compound ZeF2 dot SbF5 and ZeF2 dot AS5 exist as ionic species ZeF positive SbF negative 6 and ZeF positive ASF negative 6. The compound ZeF2.2SbF5 has been shown to contain ZeF positive and sp2F11 negative ions. The ZeF positive ions is strongly bonded to sp2F11 by a fluoride bridge between xenon and antimony. ZeF2 also react with arsenic pentafluoride in a different stoichiometry. 2 xenon difluoride plus ASF5 gives 2 ZeF2.AS5 ASF5. 2 xenon F2.AS5 exists as Zd2F3 positive ASF6 negative. The ion Zd2F3 positive has the expected linear geometry around xenon and an angular geometry around the xenon fluoride. Structure and shape of ZeF2 molecules. Stereospectral analysis has shown that ZeF2 molecules has linear geometry. This is explained on the basis of valence band theory as follows. Xenon in the ground state has a valence shell configuration 5s to 5p6 as shown in figures. One of the 5p electrons get unpaired and promoted to the 5d orbital, resulting in 2 unpaired electrons, one in 5p and one in 5d orbitals in the excited state of xenon. 5 orbitals, one 5s and 3 5p and one 5d hybridized to give 5 sp3d hybrid orbitals which adopt trigonal bipyramidal geometry. The two orbitals containing single electron overlap with two fluorine atoms forming two xenon fluorine bonds. The xenon and two fluorine atoms lie in a straight line, that is are linear, while the equatorial positions are occupied by three lone pair of electrons. The molecule has thus a linear geometry as shown in the figures. The lone pairs are present on equatorial positions of the triangle in a plane. Because of the symmetrical arrangement of three lone pairs, each at an angle of 120 degrees, the net repulsion on one pair is zero. Therefore, ZeF2 molecule is linear. The important properties of xenon difluoride are summarized below. Xenon tetrafluoride. Preparation. It can be prepared by the following methods. It is prepared in good yield by heating a mixture of xenon and fluoride in the molar ratio of 1:5 in a nickel vessels at 400 degrees Celsius under a pressure of 5-6 atm. It is also synthesized by passing an electronic discharge through a mixture of xenon and fluorine in the molar ratio of 1:2. At -78 degrees Celsius, pressure is maintained between 2 to 15 mm of mercury. Properties of xenon tetrafluoride are: it is a colorless crystalline solid. Its melting point is 117.1 degrees Celsius. It sublimes readily. It dissolves in iodine pentafluoride and hydrogen fluoride without reading. It is oxidized by hydrogens to HF at 30 degrees Celsius. ZeF2 plus 2 hydrogen gives xenon plus 4 hydrogen fluoride. It is a stronger fluorinating agent than xenon difluoride. It converts Hg to HgF2, platinum to PtF4, NO and NO2 to NOF and NO2F respectively, SF4 to SF6, etc. It reacts with boron trichloride to form boron trifluoride. It undergoes disproportionation in water, giving a highly explosive solid compound ZeO3. But if the reaction is controlled at minus 80 degrees Celsius, it forms xenon oxyfluoride. It combines with molten TaF5 to form straw-colored TaFC twice. It forms an addition compound with the antimony pentafluorides. ZeF3 positive has the T-shaped structure, trigonal bipyramidal with two positions occupied by lone pairs as shown below. Structures. The electronic structure of ZeF4 may be written as this. Spectroscopy method have shown that ZeF4 has square planar structures. This can be explained on the basis of valence band theory as described below. Xenon atom in the ground state has 5s2 5p6 outer shell electronic configuration. In the formation of xenon tetrafluoride molecule, two of the 5p electrons are promoted to 5d orbitals, so that there are now 4 unpaired electrons, 2 in 5p and 2 in 5d orbitals as shown in figure 3. The 6 orbitals 1 5s 3 5p and 2 5d get hybridized to form 6 sp3d2 hybrid orbitals. These 6 sp3d hybrid orbitals adopt octahedral geometry. 4 of these containing single electron overlap with 2p orbitals of fluorine to form 4 xenon fluoride bonds. The remaining 2 positions are occupied by lone pairs. Thus, as shown in figure 3, the molecule has square planar shape. Xenon oxyfluoride. Xenon oxyfluoride preparation. It is prepared by slow and partial hydrolysis of xenon tetrafluoride at a low temperature, minus 80 degrees Celsius. It is not a very stable compound. Structures. Spectroscopic method have shown that xenon oxydifluoride has a T-shaped structure. This can be explained on the basis of a VBT as described below. Xenon atom in the ground state has 5s2 5p6 outer shell electronic configuration. To account for tetravalency of xenon, 3 sigma bond and 1 pi bond, 2 of the 5p electrons are promoted to the 5d orbitals in excited state. In this case, the 5 orbitals 1 5s 3 5p and 1 5d get hybridized to form 5sp3d hybrid orbitals. 1 5d orbitals is left unhybridized for forming pi bonds. 3 of the 5 hybrid orbitals, which are singly filled, form sigma bonds with 2 fluorine and 1 oxygen atoms. 1 5d orbitals, which is not involved in hybridization and is singly filled, is used in forming an additional bond, which is a pi bond with the oxygen atom. There is thus a double bond, 1 sigma bond and 1 pi bond between xenon and oxygen atoms. Since the xenon oxydifluoride molecules involves sp3d hybridization, its structure should be trigonal bipyramidals, but due to the presence of two lone pair of electrons occupying two positions in these structures, there is a distortion in the molecules. The compound therefore has a T-shaped structure. Xenon hexafluoride. It is prepared by the following methods. It is prepared by heating xenon with excess of fluorine in the molar ratio of 1:20 in a nickel vessel at 250 to 300 degrees Celsius under pressure of 50 to 60 atm. It can also be obtained by oxidation of xenon tetrafluoride with the O2F2 under pressure. It is also prepared by passing electric discharge through a mixture of xenon and fluoride in the ratio of 1:3 at low temperature. Xenon hexafluoride can be separated from xenon difluoride and xenon tetrafluoride by passing through sodium fluoride, which absorbs xenon tetrafluoride at 70 degrees Celsius, giving Na2ZeF8. On warming Na2ZeF8 at 120 degrees Celsius, pure xenon hexafluoride is evolved. Properties. It is a solid crystalline substance. It melts at 49.5 degrees Celsius. It is most volatile of all fluorides of xenon. Its vapor have a greenish yellow color. It dissolves in hydrogen fluoride, giving a solution which is a good conductor of electricity. This is attributed to the formation of ions as under HF plus ZeF6 gives ZeF positive 5 plus ZF HF negative 2. ZeF6 thus differs from xenon difluoride and xenon tetrafluoride as it dissolves in hydrogen fluoride without reacting. It is reduced to xenon by the action of H2, ammonia, or hydrogen chloride. It undergoes slow hydrolysis with atmospheric moisture and form xenon trioxide, which is highly explosive. ZeF6 plus 3H2O gives ZeO3 plus 6HF. Careful hydrolysis in nickel vessels gives colorless tables xenon oxy tetrafluoride. It is extremely reactive, therefore it cannot be stored in glass or quartz vessel because of the following reactions, which finally give the dangerously explosive xenon trioxide. It reacts with fluorine ion acceptors to form adducts. ZeF positive 5 has a square pyramidal geometry. With fluoride ion donors, it forms ZeF7 negative and ZeF2 negative species. ZeF2 negative 6 ion has a square antiprismatic structure and shape of xenon hexafluoride molecule. The ground state outer shell electronic configuration of xenon is 5s to 5p6. 3 of the 5p electrons are promoted to the 5d orbital so that there are 6 unpaired electrons, 3 in 5p orbitals and 3 in 5d orbitals. In this case, 7 orbitals 1s, 3p and 3d hybridize to give a 7 sp3d3 hybrid orbitals which adopt pentagonal bipyramidal geometry. 6 of these orbitals containing single electron each are used in bonding with 6 atoms of fluoride. Due to sp3d3 hybridization, the molecule should have pentagonal bipyramidal structure, but it is slightly distorted on account of the absence of a lone pair of electrons at one position. However, there has been controversy regarding its structure. It is preferably believed to have a distorted octahedral structure in which all the 6 positions are occupied by fluorine atoms and the lone pair is present at the center, one of the triangular faces. This is shown in figure. Alternatively, it has been suggested that lone pair is present in the middle of an edge. Xenon oxytetrafluoride preparation. It can be prepared by the following method. Xenon oxyfluoride is prepared by partial hydrolysis of xenon hexafluoride. It can be prepared by the action of xenon hexafluoride on silicon dioxide. Soon as the yellow color of xenon fluoride disappears, the content are immediately quenched with solid CO2. It is done to avoid the formation of xenon trioxide. It is prepared in appreciable quantities by heating a mixture of xenon and fluorine in the molar ratio of 1:4 in the presence of a large excess of oxygen at about 230 degrees Celsius. It can be purified by vacuum distillation. Properties: it is a colorless compound melting at -46 degrees Celsius. It is reduced by hydrogen to xenon. It reacts with water or silica to form another oxyfluoride, xenon difluoride, in which xenon remains in the same oxidation state. It reacts with fluorine negative ion acceptors to form ZeOF positive 3 cations. The ZeOF3 positive cation has the following structure, in which the lone pair, the oxygen atom and the fluorine atom, occupy the equatorial position of a trigonal bipyramidal structure, and 2 fluorine atoms occupy axial positions. Xenon oxytetrafluoride react with nitrosyl fluoride to give crystalline compound NO positive ZeOF5 negative. ZeOF5 negative ion has a pentagonal pyramidal structure with the oxygen atom in the optical position. In this case, xenon atom is slightly above the plane of 5 F atoms. Structure and shape of xenon oxy tetrafluoride molecules. Xenon atom in ground state has 5s to 5p6 outer shell electronic configuration. In order to account for hexavalency of xenon in ZeOF4, 5 sigma bond and 1 pi bond, 3 of the 5p electrons are promoted to 5d orbitals when excited. The 6 orbitals 1s, 1 5s, all the 3 5p and 2 of the 5d orbitals get hybridized to form 6 sp3d2 hybrid orbitals which adopt octahedral geometry. One of the 3d electrons remain unhybridized for forming pi bonds. 5 of the singly occupied hybrid orbitals form sigma bond with 4 fluorine atoms and 1 oxygen atoms. The 5d orbital which does not take part in hybridization forms a pi bond with the oxygen atom. Thus oxygen is combined to xenon by a double bond, one of which is a sigma bond and the other is a pi bond. It may be noted that one of the hybridized orbitals contain a lone pair of electrons. The molecule has a square pyramidal structure. Xenon dioxydifluoride preparation. It is prepared by mixing ZeO3 and ZeOF4 at low temperature close to minus 78 degrees Celsius. The compound is purified by fractional distillation. It is also found when xenon oxide tetrafluoride is hydrolyzed or reacted with silica. It is a colorless solid. Its melting point is 30.8 degrees Celsius. It is hydrolyzed to give xenon trioxide. It slowly decomposes to give xenon difluoride and oxygen. Therefore, thermodynamically it is unstable. It reacts with SbF5 in H5 and gives a white solid of composition ZeO2F positive, Sb2F11 negative. The compound is unstable at room temperature and slowly decomposes to give ScF positive, Sb2F11 negative and oxygen. ZeO2F positive has tetrahedral structure in which one position is occupied by a lone pair. Structure and shape of xenon dioxide difluoride. In this case, 3 of 5p orbitals are promoted to 5d orbitals when excited. The 5b orbitals 1 5s 3 5p and 1 of the 5d orbitals get hybridized to form 5 sp3d hybrid orbitals. These adopt trigonal bipyramidal geometry. 2 of the 5d orbitals are left unhybridized for forming pi bonds. The 4 hybrid orbitals forms sigma bond with 2 fluorine atoms and 2 oxygen atoms. The remaining 2 singly filled orbitals which do not take part in hybridization form pi bond with the same 2 oxygen atoms. Each oxygen atom is thus bonded to xenon atom by a double bond, one of which is a sigma bond and the other a pi bond. It may be noted that one of the hybrid orbitals contains a lone pair of electrons. The molecule does not have a regular geometry. There is, however, a slight distortion due to the presence of a lone pair in one of the equatorial positions. Xenon trioxide is prepared by the hydrolysis of xenon hexafluoride or xenon trifluoride. However, the last reactions proceeds through the following stages. ZeF6 plus H2O gives ZeF6 plus H2O gives ZeOF4 plus 2HF. ZeOF4 plus H2O gives ZeO2F2 plus 2HF. ZeO2F2 plus H2O gives ZeO3 plus 2HF. Great care should be taken during its preparation because it is highly explosive. Properties. Xenon trioxide is a white non-volatile solid. It is soluble in water. It is quite stable in aqueous solution. However, it explodes violently when dry. It acts as a powerful oxidizing agent in acidic medium. For instance, it oxidized PO3 positive to PO4 positive in the presence of H positive ions. The advantage of this reaction is that the only byproduct is xenon gas, which being inert does not introduce any extra complicating reactions. It also reacts with potassium iodide, giving 3 moles of iodine per mole of xenon trioxide. It undergoes disproportionation when dissolved in sodium hydroxide and forms sodium persaicnate. The X-ray analysis of sodium persaicnate reveals the existence of the octahedral persaicnate in ZeO6 4 negative in the substance. Sodium persaicnate, when dissolved in an acid solution, decomposed slowly to give xenon trioxide and oxygen. It reacts with xenon hexafluoride and xenon oxide tetrafluoride. Structure and shape of ZeO3 molecule. Structure and shape of xenon trioxide molecules. Xenon in the ground state has the outer shell electronic configuration as 5s to 5p6. In the formation of xenon trioxide, 3 of the 5p electrons are promoted to 5d orbitals. The 4 orbitals 1 5s and 3 5p hybridize to form 4 sp3 hybrid orbitals which adopt tetrahedral geometry. 3 electrons on xenon remain unhybridized for forming sigma bonds. 3 of the 4 hybrid orbitals which are singly filled form Three pi bonds with three oxygen atoms. The three unhybridized 5d orbitals form three pi bonds with the same three oxygen atom. Thus, each oxygen atom is bonded to xenon by a double bond. One of the hybrid orbitals contain a lone pair of electrons. Consequently, the molecule, instead of being tetrahedral, has a pyramidal structure. Xenon 8 compounds. Although there have been some reports of compound of xenon in 8 oxidation state, yet these not have been confirmed by more recent works. The common compounds suggested are ZeF8, ZeOF4, ZeOF6, ZeO3F2 and ZeO2F4. ZeOF4 has been prepared by the action of concentrated H2SO4 on sodium or barium xanate. It may be purified by vacuum sublimation at -78.3 degrees Celsius. It is unstable and decomposes to xenon and oxygen. It is very explosive and explodes even at -40 degrees Celsius. It has the tetrahedral structures, compound of other noble gases. Recent experiments have shown that krypton and radon can also combine with fluorine under suitable conditions, yielding krypton difluoride and krypton tetrafluoride and radon difluoride, krypton difluoride preparation. It is prepared by irradiating a mixture of krypton and fluorine at a very low temperature, -193 degrees Celsius. Irradiation can be carried out by gamma rays, UV light, or by electric discharge. Properties: krypton difluoride is a colorless solid. It is easily hydrolyzed. It is a powerful oxidizing and fluorinating agent. It forms adduct with SBF5 and AS5 structures. The structure of krypton difluoride is similar to that of xenon difluoride. It also involves sp3 dehybridizations of 5p orbital, 4s, 3, 4p and 1, 4d. Two of these hybrid orbitals form from sigma bonds with two fluorine atoms, and three positions are occupied by lone pairs. The geometry is linear. Krypton tetrafluoride and oxides have not been claimed definitely. Radon difluoride can also be prepared by similar method. However, it is highly unstable. Are compound of helium and neon possible? In normal state, all the s and p orbital of xenon, krypton and radon atoms are fully filled. However, there are vacant d orbitals in the valence shells which allow for the promotion of one or more electrons from d orbital for the formation of unpaired electrons. If this be the case, it seems that helium and neon will never form compounds because they have no d orbitals at all. The promotions of electron from s or d orbitals to next shell is highly unfavorable. Moreover, the ionization energy of helium and neon are considerably higher than that of xenon and krypton. This fact also rules out the possibility of the formation of compounds of helium and neon even with fluorine and oxygen. Thank you.